Good day to all of you. My name is Eveline Volcke, and it is my pleasure to present to you today some of the research work that we do at our faculty. I will talk to you about digital water, and I will do this together with my colleague, Elena Torfs. We will provide you with an overview fitting into the Capture initiative on sustainable resource recovery, which is carried by UGent and partner institutes in Flanders. Capture promotes collaboration between various research teams and is organized according to three main pipelines: water fit for use, plastics to resource, and CO2 to product. The researchers in each pipeline have defined programs which they want to work on, and digital water is one of them. Digital water, as we see it, comprises monitoring, data handling, and modeling for decision support and for process optimization. Since it is the digital water program, we clearly target applications in the water sector. Let me start by giving you the practical example of wastewater treatment. Wastewater treatment processes are facing increasing demands, which go beyond guaranteeing the effluent quality which is required today. Wastewater treatment plants face load increases and stricter effluent quality limits. They are confronted with space limitations, and moreover, they need to be energy efficient, they need to be sustainable, and they need to aim at resource recovery. All of these goals need to be addressed at once, and there is a clear role of adequate monitoring, data handling, and modeling to achieve it. Monitoring involves the development of measuring techniques. We perform off-gas analysis to measure the concentration of, for instance, greenhouse gases such as N2O, methane, and CO2. In case of an open process, a sample of the gas phase is taken with a floating hood, which is connected to an online gas phase analyzer. By measuring oxygen, we can also determine aeration characteristics. But we can do more than that. By combining the gas phase measurements with our process knowledge and with mass balances, we can also calculate dissolved gas concentrations, conversion rates, and waste sludge production, which are variables that are very hard or even impossible to measure in practice or directly. But monitoring is more than just measuring things. We need to be sure to measure the right things. There are often a lot of variables which could be measured, for instance at wastewater treatment plants. But there is only a small fraction of the measurements which gives us the useful information we are looking for. If you measure too much, you lose money. But it may be even worse if you measure a lot and still miss out on some crucial information. We apply experimental design to optimize the sensor network and to set up measuring campaigns. The result is given in the form of Pareto optimal sets of additional measurements which balance costs, which is the number of measurements, and accuracy. Measuring the right things allows water practitioners to monitor the process performance with minimal cost. In such sampling design, one decides how many samples need to be taken and where and how much variability is allowed in these measurements to be able to decide whether or not the process is under control. However, often performance variables cannot be measured directly. We then aim at monitoring them indirectly through what we call soft sensors. For instance, the quality of the product or the processed water can be measured directly, and then data-driven models can be applied to estimate the variables of interest. Such data-driven models, however, need frequent calibration to stay up to date. By applying optimal experimental design theory, we can determine which measurements to take to minimize the calibration efforts and costs. All of our monitoring actions produce data, and the statistical analysis of these data is essential to inform us of the uncertainty during decision-making. It is crucial to have reliable estimates of the variability that is expected in the measurements and to detect when this variability is increasing, for instance. In case there is only one variable, a number of standard models can be used. However, in practice, we are often interested in multiple variables which depend on each other. An example is given by a sensor network which follows concentrations at several locations in a wastewater treatment process. We then take into account the dependency between the measurements to detect deviating trends, patterns, or extremes and anomalies. Data are not only applied for decision-making, but also for assessing process performance and for retrofitting and cost reduction. Data are also used for modeling. But you may have the greatest model ever. If you put garbage data in, what you will get out is garbage. We apply data reconciliation, another statistical tool, to improve the quality of the collected data, to detect inconsistencies, to improve the measurement accuracy, and even to calculate unmeasured variables. This is comparable to what is done with soft sensors and then data-driven models.
Hello, my name is Elena Torfs, and I would like to take a few more minutes of your time to tell you a bit about the modeling research that we're doing at our faculty related to the water sector. So when we talk about digital water, we talk a lot about data and data abundance. And then, of course, we run into hot topics such as artificial intelligence, machine learning, or other type of data-driven modeling techniques. These are very, very powerful tools to transform the abundance of data that we're collecting into decision support. But of course, on the other hand, we are not only measuring our systems, we also know them. We understand the physics, the biology, the chemistry behind our processes. Maybe not in every detail, maybe not perfectly, but we know a lot. And we can use this process understanding to build so-called mechanistic models. So mechanistic models where we construct mathematical equations based on the physics, the chemistry, and the biology of our system that we know. So we have these two types of modeling frameworks. On the one hand, we have the mechanistic models, where we put in our process knowledge, and on the other hand, data-driven models, where we put in a lot of the data that we're collecting. Which brings me to an important research question, I think, and something that we are looking into with a lot of interest, is how can we make sure that we leverage both of these modeling paradigms in an optimal way, that we use the power of both of these type of models as much as possible, and that we find a way to combine them in an optimal way. So that brings me to the topics that I want to discuss here, which is hybrid modeling. And that is, how can we indeed combine these physical process models, mechanistic models with data-driven modeling technologies. So I'm going to show a very simple example to illustrate this. So on this graph, you see the nitrate concentration in the effluent of a wastewater treatment plant. So the dots show the measurements of an online sensor, and then the full line shows you a prediction of a mechanistic model that we've developed. You see that this model is not perfect. For instance, especially here, the peak concentration is not so well predicted, but in general, it's doing not that bad. Okay, we could also do this through a data-driven model, where we use a lot of our plant sensor data, we train a model, and then we use that model to predict our nitrate concentration in the effluent. So this is an example where we use a data-driven model, but this model has only been trained on dry weather data. So here, the gray area where we see that there's a rain event, conditions change in the plant, we see that when there's no rain in this first part, the data-driven model is almost perfect. This peak is captured almost perfectly. But once we submit the model to a condition that it hasn't seen before, where it hasn't received data for, that it hasn't been trained for, this rain event, then of course it loses its predictive power. This brings us to the danger of data-driven models, that it's incredibly powerful as long as we stay within conditions where the model has been trained for. And then, of course, we can see, can we not combine both paradigms into a hybrid model? And that is what you see here, where we obtain a model that consists of both a mechanistic model and a data-driven part, and that is so able to really, really well predict our peak behavior here of nitrate concentration in the effluent, and that is still able to capture all the other trends throughout both dry weather and rainwater. So this is a topic of a lot of interest. These hybrid models, you can combine mechanistic models and data-driven models in many different ways. In this specific example, we used neural ODEs, where we combine ordinary differential equations with a neural network. The second aspect that I want to bring to your attention here in this presentation is the increase in computational power that we have at our disposal. This allows us to develop and simulate very advanced models. And with advanced models, I mean, of course, very computationally expensive models. The example here on this slide, for instance, shows a computational fluid dynamics model of a dissolved air flotation reactor. And you see the hydraulic residence time of the air bubbles throughout the reactor geometry. And each of these graphs then shows how the hydraulic retention time of the bubbles will change when we consider a different bubble size. So these kind of advanced models, they give you very detailed information on what is happening inside your process or inside your reactor. So we can use them to build system understanding and then maybe improve your design or certain operational features. But we can also see these advanced models as an additional source of data. Simulated data, yes, but still data. And actually data that is very difficult to come by with a physical sensor, or you would have to place sensors, a whole lot of sensors throughout your entire reactor. So I think here again, it's important to reflect on the synergy between data collection, data-driven techniques, data analysis, and first principles models that actually give you a lot of knowledge based on the process knowledge that you put in there. Let's look at another example on this. So let's go back to a wastewater treatment plant. And actually what I want to look at with you is one of these bioreactors that are I-rated and in which organics and other compounds in the wastewater are actually degraded by activated sludge or microorganisms. So we've developed a CFD model for this reactor. So for one of these circular bioreactors, and the graph, the figure here shows the oxygen concentration throughout this circular reactor. You see that this is quite heterogeneous. So depending on where you are in the reactor, your oxygen concentration will be very different. The X indicates the sensor locations. So if you actually measure oxygen, you will only have one very specific aspect of this heterogeneous behavior. So what we can then do is, just as an example, so we have the CFD model that gives you the DO profile and the heterogeneity over this entire reactor. So we have then the DO concentration in each of these locations throughout the reactor. And this we can use as input to a simple data-driven model. Here we have a model that for N2O risk analysis. And this N2O risk model, it's a knowledge-based model. So it uses fuzzy logic behind it. But this would allow you, by using your very detailed CFD model that predicts your DO concentration at each location, to then input this to your N2O risk model to actually predict a risk of N2O formation, so an important greenhouse gas, at each location in your reactor. Whereas you can imagine if we would use DO data from the sensor, we would only get the risk at that one single point in the reactor instead of throughout the entire reactor geometry. So let's have a look at what this gives us as a result. So here you see a part of this circular reactor again, and you see that indeed the risk of N2O formation changes a lot throughout this reactor, where we see here in blue very low risk, whereas in the red zones we have a very high risk of N2O formations. This is about all that we have time for today. Thank you for your attention. If the presentation that we gave here has brought up any questions or any further interest from you, don't hesitate to contact us to learn more. You can contact me or any of my colleagues here on this slide that have contributed to this presentation. Thank you very much.